So here we are at my favorite beach, downtown Toronto's only beach. I've got my chalkboard. I got a brand new chalkboard. Got some Hagoromo chalk. I can use this as extra note paper. I'll use the back of this rather than throw it away. This plastic, I guess I'll get rid of that. There's garbage cans over here, emptied regularly. That garbage can is emptied regularly also. So now let's take a look at Fourier analysis. So I'm going to do a two-part lecture on the Fourier Transform and the Fourier operator. So the Fourier Transform is defined as the integral from minus infinity to infinity of some function g of t, let's say, times e to the negative 2 pi I times ft dt. And we'll usually use capital letters like g of f is equal to that. So g of f is equal to the integral from minus infinity to infinity of g of t times e to the minus 2 pi I times ft dt. And that's, in a sense, an inner product. It's more or less an inner product of g of t with e to the plus 2 pi I times ft, this wave. And by definition, this is a minus. We put the minus sign in this part so that when we take the Fourier transform of some signal, if g of t was a complex exponential, 2 pi I times some carrier frequency times time, when this frequency equals that carrier frequency, then the result is a Dirac delta measure at that frequency. So what that in a sense does is it tells us how much of each frequency component is present, because this thing here, e to the minus 2 pi times f times t, this thing right here is a signal. It's a waveform, minus I 2 pi ft, or e to the minus 2 pi I, sometimes we write it like that, times f times t, is a wave. And as a wave, its part, it's equal to cos 2 pi ft plus I times sine 2 pi ft. So it's a wave whose real part is a cosine and the imaginary part is a sine. And so we can think of that, if we think of this on the Argand plane, if we look at what this wave is doing, and usually we have a negative in here in this part of it, when we're considering, because we define positive frequencies as counterclockwise in the Argand plane. So if this is the real axis and this is the imaginary axis, what happens is when you put that cosine, if the real part, if you basically take an XY plotter, if you take a machine designed for drawing graphs, such as an oscillograph from the 1930s, and this is from the Latin word oscillum, which means to swing, and the Greek word graph, which means drawing or painting. And in more modern terminology, we often use the word oscilloscope to be purely Latin. And this is all Latin, and that's kind of the modern term that people often use, is basically a machine for drawing graphs. It's a device that plots things, and you put voltages into it. So it looks like this. An oscillograph or oscilloscope looks like this, typically, and there's typically a screen on it. In the older ones, they're round screens, and the newer ones tend to have rectangular screens. And you'd have an input, an X input and a Y input, and these are connected to deflection plates. You have a glass tube. It's a glass CRT. It's a cathode ray tube that looks like this. It's a glass evacuated tube, and you've got phosphor, like what you have in a fluorescent light. Actually, one of my students, when he was 12 years old, he built one of these out of a glass tube and some phosphor from a broken fluorescent light bulb, put it on a piece of glass, and he had a vacuum pump and he sucked all the air out of it. He built the particle accelerator and everything when he was like 12 years old. It was super amazing. Adnan was his name, and a super genius, one of my students. And so if you're not a genius like Adnan, you buy one of these somewhere rather than make it. And it has pins on it, connectors on the base that connect to voltage, and there's a little, you'll have a little particle accelerator here with a hole in it. This is the anode, and the cathode here. And typically for a 5-inch tube like the one I have in my lab, it'll be about 2,600 volts or so. So the voltage, there's about 6.3 volts on that filament, and the heater here, it heats it up. Electrons are emitted from it, and there's about 2,600 volts here. The electrons are accelerated towards this thing, and of course some of them keep right on going over to this screen, and they produce a little dot on the screen, a glowing dot. And typically this phosphor is made out of something that glows green, with the original invention of oscilloscopes. And then when television was invented, they preferred to use a white glow so that you could produce a natural grayscale image, and later of course color TV. But initially you have that green glow here, and then there's deflection plates or coils. You can magnetically or electrostatically deflect the electron beam. You can put a magnet here and it'll deflect the beam, so you can wind a coil of wire. And what Adnan did is wound some coils of wire around some metal objects to deflect the beam with an input signal, so you could put a voltage in here and draw the graph of the voltage. But preferably you have deflection plates because they're more linear over a broad range of frequencies. You'll have horizontal plates and vertical plates. Usually the vertical plates come first so that you've got more sensitivity to the vertical input, and the horizontal is usually a sweep generator, which can have a stronger output. And so as you apply a voltage to these plates, it deflects the beam. So typically you have these two inputs, X and Y. The X input here deflects the beam this way, and then that's a set of plates that are like this, and the Y input goes to a set of plates over here that deflects the beam that way. So this one here and that one here, this one here and that one here. And some of the older oscilloscopes, they have a setting on the front that little switch, a little click switch that allows you to directly connect these input terminals to the deflection plates on the cathode ray tube. And in another setting, it goes through an amplifier to boost the gain on it. But you have an XY plotter here, and this plotter, one of the simplest things that you can plot is to let X equal cos 2 pi times some carrier. I'll take it, say f sub c, meaning a specific carrier frequency times time, and let Y equal sine 2 pi fct. And now we plot this graph. Now what do you think that shape plot will be? If we put a cosine in here and a sine in here, of course it'll draw around in a circle, and it's nice to have a round screen with a circle on it. It looks quite nice for Pi Day especially. You can have your round screen here, and then you've got a circle on the screen, and the dot moves around in a circle. The dot follows the path of a circle because it's driven by these sines and cos. And as you increase the frequency, it goes around faster and faster. And in fact, you can measure the bandwidth of the oscilloscope by measuring how fast it reports the circle. An interesting question is, how fast can you turn that circle and still distinguish counterclockwise from clockwise? An oscillograph or oscilloscope is a machine for plotting graphs. And typically we have waves, like the waves out here in the lake. These are waves. This is fundamental physics here. We've got these beautiful waves out here, and if you look at these waves, they're not exactly periodic, but they rise and fall. There's a wave coming and then another one coming. They're not perfectly sinusoidal, but you could break them down into a combination of sinusoids. We could say, in a Fourier sense, we might break it down into a Fourier series representation and say that we could represent these waves, say whatever that shape of wave is equal to a whole bunch of sines and cosines added together to make a wave that has that same shape. So that's the beauty of this kind of representation. It can represent a wide range of different kinds of functions, different kinds of wave shapes. And so now getting back to this example of waves here, what we have is, we have this wave, the cathode ray screen forms a circle, and one way to think of it is to think of this axis as the real part. So say we have some complex number, z equals x plus I, y, where I equals the square root of -1. Now we have this as the Argand plane. This is called the Argand plane, or the complex plane. And this is the real part, and this is the imaginary part. And the magnitude, the length of this distance from the center is the square root of x squared plus y squared, and the phase equals arctan of imaginary over real, y over x. And so that's the angle that we go here. And we define positive angle as going counterclockwise. So now you have this wave here that is moving around, that dot's moving around in a circle. And now you can tell the difference between a positive frequency and a negative frequency because a positive frequency goes counterclockwise in the circle, and this is a positive frequency here. This has positive frequency components. But if we had another signal that maybe looked like this, if you had something like x2, let's say, equals, and say this is x1, y1, x2 is equal to sine theta, sine 2 pi fct, and y2 equals cos 2 pi fct, for example. We reverse the roles of sine and cosine. Now that one, that's going to go clockwise in the plane. It's going to go this way, and so this is a negative frequency. So if I say z2, I define z2 equals x2 plus I, y2. We say the frequency content of z2 is negative. So if we look at this, if we look at the spectrum here, 0 is in the origin, and z1 has this frequency spectrum, and this is the carrier frequency fc, and this is the frequency f. And we look at z2, z2 has this frequency spectrum, and it has negative fc as the frequency content, and this is the frequency f. And so you can see that these, and there's a phase shift, of course, this is the magnitude, but there's also a phase shift to be considered in the Fourier transform. So you can see here that we have a concept of negative or positive frequency that becomes visible or knowable when we have a complex valued signal. If a signal is real, it must have the eigenfunctions or an emission operator are real, more in general. Specifically, though, if a signal is completely real, its frequency spectrum must be, Hermitian symmetric about the origin. So the power spectrum, it's going to have the same amount of energy here as it does over here. If you look at the amount of energy, whatever energy is present here is over here. So if you have like a 60 hertz electrical socket, you've got this socket that looks like this, and in the old days they looked like that, and nowadays sometimes they put them upside down. So you might see this thing look like this. And so there's an electrical socket, there's a ground, and there's two wires here, and there's a voltage and the voltage as a function of time looks like this. Depends on when you start measuring it. There might be phase shift. It might look like sine or cos or any other wave. It could start at some arbitrary phase, but it's going to just be a wave like this, and it has both positive and negative frequency components to it, meaning it doesn't turn in the Argon plane. It doesn't forcibly go around in a particular way. But when you have, for example, if you have three-phase power, what they do is they have three electrical wires that are 120 degrees apart, and maybe one here, and one here. This is 120 volts. The radius of this circle is 120 volts, and this is, 208 volts. And so that's the square root of 3 relationship between them. And so what you have there is you've got three-phase power, and the frequency spectrum of a three-phase socket looks like this. Over here you've got at 60 hertz. All the energy is here, and none of the energy is over here. So what that means is that it decisively has a positive frequency component, and that's called a progressive signal. Something is said to be progressive when it only has positive frequency content in it. So the Fourier transform, g of f, equals the integral from minus infinity to infinity of this thing g of t times e to the negative 2 pi I ft dt. It's defined that way with a negative sign in here because we want to correlate the negative frequency with the positive frequency, so that when there's content that has a positive frequency, in other words, if something's rotating clockwise, if, let's say, g of t, let's say this is a signal, a three-phase power line that's at exactly 60 hertz or something like that, that has nothing, as zero over here at this side, just totally zero on the negative frequencies, and only has positive frequencies in it, then it will be something of the form, let's say, g of t equals e to the plus 2 pi I times some carrier frequency, say fc times t. And so then you're going to have the g of f is equal to the integral of e to the plus 2 pi I times the carrier frequency times time times e to the minus 2 pi I times f in general times time. This is the carrier frequency fc, and this is the general frequency f dt. And what happens is that equals a Dirac delta measure. These exponents subtract. So when fc equals f, that gives you, an infinite amount at just that one infinitesimal point. So if you look at g of f as a graph here, it's just going to, when f equals fc, so when the frequency f on this axis equals fc, it shoots up to infinity there for an infinitesimally short duration, so it has an energy associated with it. That's called a Dirac delta measure, and it's zero everywhere else. It's not a function. So it's only a measure. It only has meaning under the integral sign. But that sign convention is used so that a signal with positive frequency energies, Fourier transform, has positive energy content. And then, so we've got g of f equals the integral of g of t times e to the negative 2 pi I times f times t dt. And then the inverse Fourier transform, if we want to come the other way, to recover or come back. When we transform this signal, we want to come back. So g of t equals, and this is the integral from minus infinity to infinity. That's the integral of g of f. And this time it's e to the plus 2 pi I times ft df this time. So we're integrating away frequency, and it's the integral from f equals minus infinity to infinity. And so now I've just put a plus sign here. Obviously you don't have to put the plus sign, just to emphasize that this is positive and that's negative. And so now you can transform something into the frequency domain and then transform it back again. And it's integral. It's useful to think of this as an operator that acts on something. So we define this. We often define this as say script f times g of t is this operator that acts on it, gives us g of f. We'll think of this Fourier transform as an operator. In discrete case, discrete Fourier transform, this operator is just a matrix and this is just a vector. And in that case, it's just matrix multiplication that provides this operation. In the continuous case, this is, an integral, and this is a Fredholm integral, and this is the kernel of the integral. That's called the kernel of the integral. It's kind of analogous, I guess, loosely speaking, as if it was an infinity by infinity matrix multiplied by this infinitely long data vector. And of course, there's special cases like the DFT, the discrete Fourier transform, where we can think of this as a discrete case, where you can think of it as a matrix multiplication. You've got elements in the matrix. So, the simplest case is a 1 by 1, where it's just a 1 and it's a 1 by 1 matrix times 1 sample long. The signal, it is the Fourier transform. Whatever you do is the Fourier transform. For the two-dimensional discrete Fourier transform, you might have 1, 1, and then 1 minus 1. And then whatever the signal here is, G1, G2, and this is your big F, the Fourier operator, times this signal is equal to big G1, big G2. And the first entry is just the DC component. It's just the sum or the average. We might have 1 over root n, where n is the number of data points, n equals 2 in this case. If we want to preserve the energy in the physical domain, equals the energy in the Fourier domain, Parseval's theorem. Parseval's theorem, which says the amount of energy in the physical domain should equal the energy in the Fourier domain. More generally, sometimes we call that Plancherel's theorem in general for transforms beyond just the Fourier transform. And so, however, the normalization you have out the front, sometimes they put that in, sometimes they don't. But you should bear in mind that there's going to be some renormalization. The inverse Fourier transform will have a 1 over n in it then, or the forward, or you might have 1 over square root of n on both the inverse and the forward, however you want to do this. But the important thing to keep in mind is that the first element of the discrete Fourier transform here, G1, is just the DC. It's just the total or the average, or it might be 1/2 of G1 plus G2, depending how you normalize, or just G1 plus G2, or G1 plus G2 over root 2. So it'll be proportional to the DC in the signal, and this is the alternating current. This is the difference, G1 minus G2. So G1, is equal to some constant alpha, whatever your normalization is, G1 plus G2, and G2 equals some alpha G1 minus G2. So this is giving you the DC and the AC, direct current and alternating current. It's very simple with just two elements. And then you can have the 3 element Fourier transform and the 4 element Fourier transform. So you have something like this, and equals something like this. You have a vector, and then this Fourier integral, this in some sense is the sines and cosines. So the first row of this is the DC. The second row of this is is a wave, and it's a wave of negative frequency. So let's say you have a cosine part. You can just have one cycle of a cosine, and then negative sine, and then draw that a little bit better, negative sine, and then this one here will be, in general we're going to have some array. This will be 2 cycles, and the next one will be 3 cycles, the next one will be 4 cycles, and so on. And then depending on how you sample this will be a square array, a square matrix, whose rows, the real part of whose rows are sampled cosines, and the imaginary part of whose rows are sampled negative sines times -1, because we got the -1 built into the transform. And so when you multiply that, one way to think of it is that there's all these different waves in here, and then when you have some waveform under test, if I plot it sideways, let's just be silly here and have some fun, because we're at a beach after all, and we're going to have some fun here. So I'm just going to be silly and draw this wave sideways. So this is, say this is my electrocardiogram. It's going to come up like this and like this, and that's in there, and I want to compute the Fourier transform of my electrocardiogram. So this is just a list of numbers that you could put into a vector down a long column. They're going to multiply it by a square matrix, and the result's going to be a new set of numbers that's of the same length as the old set of numbers, and that's called the Fourier transform of it. And it'll show frequency components, and it'll have it'll have some peak here, and then it'll probably fall off a little bit to higher frequencies. But the heartbeat's almost like a Dirac comb, almost. And the Fourier, there's 2 functions that are eigenfunctions of this f. This thing f there's 2 kinds of functions whose Fourier transform is the same as what you started with in continuous Fourier transform, and that is a Gaussian. The Fourier transform of a Gaussian is a Gaussian, and the Fourier transform of a Dirac comb is a Dirac comb. And a Dirac comb is a bunch of Dirac delta measures, and these go up to infinity. And a heartbeat's really close to looking like a Dirac comb. So what I'm trying to say here is that when you do the Fourier transform of a heartbeat, it's going to have a lot of high frequency components. It's going to kind of give you, it's almost going to be comb-like in some sense. So it'll reach way out. It's going to have a lot of high harmonics in it. If it's periodic, it's going to have these harmonics. Of course, if it's chirping, it'll spread out a little bit. And you need to use the chirplet transform to compactify the transform space. But let's assume for the moment the heart rate's not varying and it's a constant heart rate. Then, of course, we're going to have something that is a pure line spectrum like this. So you got this matrix multiply. You're going to multiply this by this and get this. And of course, there's more efficient ways to do it than just multiplying the matrix. Your FFT, fast Fourier transform, takes redundancies, takes advantage of redundancies in that waveform signal. But in any case, you're going to have something comes in, you analyze it, and look at the frequency content in there. So here I am at one of my favorite swim spots, and watch the sun go down. Beautiful sunset. So when we look at the DFT, so let's say we had the first row is just DC component. The second row is going to be, and the first column is also DC, and then the second row, if we look at this in the Argon plane, one way to look at it, one way to think of it as, it's just, these are all just in the Argon plane, and then we're going to look at negative, so it's going to go to positive frequency, so it's going to go like this, and then like this, and then like that, and then it's going to go twice as fast, this, this, and then it's going to come around the other way. So it's going to be, so you can see this, the real part of that is your cos wave, and the imaginary part is your sine wave. And in this case, for zero frequency, the real part of cos zero is, the real part is cos zero, which is always 1, and the imaginary part is sine zero, which is always 0. So the first row is 1s, and the first column, the rows and columns are following the same pattern. So now we got 1, and then this one, we have this one pointing down. We have negative I, negative 1, and I, where I equals square root of minus 1. And then we have here, we've got 1, negative 1, 1, negative 1. This is the maximum frequency rate at the Nyquist rate, and then it rolls back around. And then we've got, you know, I, negative 1, negative I. So it's going around. So you can see this first row of the DFT matrix is just the DC component. The second row is negative frequency. So it's the cosine wave is like this, and the sine wave is like this. And you can see that's the real part and that's the imaginary part. So here the real part's 1, imaginary part's 0, and then we're going to take it at the next sample. The real part's 0 and the imaginary part is minus 1, and then here the imaginary part is 0 and the real part is minus 1. That's here. And right here at this point the real part is 0 and the imaginary part is 1, so that's equal to I. So you can see, and then the next wave here, this is right at the Nyquist rate, right where we're sampling a sine wave, and that's going to be 2 cycles of a sine wave that we're sampling. And so right here you've got a sine, you've got a cos wave, 2 cycles of a cos wave, 1, 2, and then we're going to have again 2 cycles of a sine wave. There's one half cycle, the other half cycle, the other half cycle, the other half cycle. And you can see here that the samples are falling, so that they're falling right at the 0 crossings of this sine wave. So the imaginary parts are all going to be 0, and the real parts alternating 1, minus 1, 1, minus 1. So you can see that's right at the Nyquist rate, and then it wraps around, and then it's at if you look in terms of frequency. So you're starting here. That's this row, and then we move down to here, that's this row, and then we move over to here, that's this row, and then by the time we come all the way back to here again, negative 3/4 is the same as positive 1, so this is positive 1/4 of a turn in terms of the frequency. So this is actually a positive frequency. So if you look at how that is you've got, you know, DC is here, and then slightly negative frequency here, and then even more negative to the point where you can't tell the difference between positive and negative frequency. Here it's right at the Nyquist rate due to sampling, and then here slightly positive frequency, again it wraps around. So now this matrix multiplied by any input vector, you know, G1, G2, G3, lowercase g1, lowercase g2, lowercase g3, lowercase g4 equals g1, capital G2, capital G3, capital G4. These are the entries of the discrete Fourier transform. And so when you multiply by this matrix, it converts this to this. So if we write that again using the Fourier operator, Fg equals big G. And so whatever we put here, we multiply it out, we get whatever's there. So let's take a simple example here. Let's say We'll take a simple function like 5, 6, 7, 8 is equal to, well, the first one is just the sum of those all. 5 plus 6 is 11. 7 plus 8 is 15. 11 plus 15 is 26. And then the next one is this minus this, 5 minus 7, which is negative 2. And negative I times 6 plus I times 8. So that's negative 2. Negative 2, 5 minus 7, plus 8 minus 6i plus 2i. And the third entry is given by this third row times this thing, so it's 5 minus 6 plus 7 minus 8, which is negative 1 plus negative 2, so it's negative 2. And then here we've got 1 times 5 minus 7. 5 minus 7, so that's negative 2. And this time we've got 6 minus 8i, so it's negative 2i. And notice how the real part is symmetrical about this center point. 26 is the DC component, and there's symmetry about the Nyquist point of highest frequency. The real part's symmetric there, but the imaginary part is anti-symmetric, and we call that Hermitian. So you see this is a Hermitian function. So we can write, f times 5, 6, 7, 8 is equal to 26, negative 2 plus 2i, negative 2 minus 2i. That's the Fourier transform of a 4-point long function. This is the Fourier transform of a one-dimensional signal that has a length of 4 samples, discrete Fourier transform. And it's discrete in time and discrete in frequency, so it's the domain and range are both discrete. Let's do another example here. And music even is a good example of Fourier analysis. When ice chimes, I say it's pagaphonic, a word I made up from the Greek word for ice, pagos, and phonos. So a word I made up, of or pertaining to the musical sound of ice. When ice fragments clang together and make a musical sound, it's almost harmonic in nature. Anything that has this form e to the 2 pi I times some carrier frequency times time, anything that's kind of approximately described by that oscillatory behavior, a musical tone, for example, is perfect for this kind of analysis. Let's say we took this F matrix. I'll just call it F8, meaning the 8 by 8 version of it, and draw it out here. The first row of it, of course, is all going to be ones. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8 ones. 1, 2, 3, 4, 5, 6, 7, 8 ones here. and inside this matrix here, and then that matrix is going to be multiplied by, your f, your operator f, the Fourier operator f, is going to multiply by some signal g, lowercase g, to produce the big G, capital G, which is the Fourier transform of little g. And so now the first entry is, the real part is one cycle of a cos wave that's sampled, across at 8 points, and the imaginary part is one sample of a negative sine wave that's sampled at also the same 8 points. And so one way to think of this is just draw it in the Argon plane what it's going to look like. So it's going to look like, I'll draw it as a circle with a center, and I'm just drawing it as a vector, so it's going to point 1/8 of the way around. So this is to the right. I'll draw this. If I just draw this as a circle that's pointing to the right, that's a 1 in the Argon plane. This is, negative. The value right here is negative root 2 over 2 or plus root 2 over 2 minus root 2 over 2I. So it's, which equals to 1 minus I over root 2. That's what this equals here in terms of what that is. So I've just draw that as just a circle with this arrow, and then the next entry is the arrow just moves over more, and the next one. So I'll just even draw these as vectors. I don't even need to draw the circle there. We understand what that is. So that's this vector. All the entries in this matrix have a magnitude of 1. So the only thing that matters is the phase. So all we care about is the direction of the vector. So that's this direction, and then now the vector points this way. 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 Now the vector points that way. Now the vector points this way, and finally the vector points that way. And it's almost to the point of, if we continued, of course it would come right back to where it started again. But it starts from where it's like counting in C rather than Fortran, where we go from 0 to n minus 1 rather than from 1 to n. So we're going from 0. So if we just take this little number here and we raise it to the exponent of 0 and put it here, and we raise it to the exponent of 1, in other words, just put it directly here, we square it, put it here, cube it, put it here, to the 4th here, to the 5th here, to the 6th here, to the 7th here, so 0 to 7. So we could have written that as this little thing, I'll call it W, W to the 0, W to the 1, W squared, W cubed, W to the 4th, W to the 5th, W to the 6th, W to the 7, where this W here is equal to just this vector, and W to the n equals, this vector to the n, which is equal to, 1 minus I over root 2 to the n. And of course that depends on what the scale factor out front is too. Overall there's a scale factor that we're kind of ignoring here just for simplicity. To follow Parseval's theorem, we might want to make this thing isometric and have it have unit energy, so that the energy in the time domain is the same as the energy in the frequency domain. So that's a whole other thing. And then here we're going to just go around twice as fast. We're going to have 2 samples of a cos wave. So we're going to have like this, 1, 2 samples of a cos wave, and then 2 samples of a negative sine wave. And at the first part here, it's just 1, and then we're going to sample it and sample it. When we sample 2 cycles of a wave, it's going to go around twice. So it's just going to be twice as much. So it's going to be W to the 0 is 1. Always all these left-hand entries are W to the 0, but then this is W to the 2. W, there's a nice landing. W to the 4. W to the 6. W to the 8. W to the 10. W to the 12. And W to the 14th. And then here it's going to be 3 cycles of waves, so it's going to just come around 3 times. So it's going to be W to the 0, W to the 3, W to the 6, w to the 9, w to the 12th, w to the 15th, and so on. And then the next row is going to be, w to the 0, w to the 4th, w to the 8, w to the 12th, and so on. And then this row is, w to the 0. And you can see this pattern here. And you can see the columns are the same as the rows in a sense. You can see this pattern 0, 1, 2, 3, 4, 5, 6, 7. And this is w to the 0, which is 1. W to the 0, and so on. You can see this very simple pattern of numbers that all have a magnitude of 1. And then this is w to the 0, to the 1, to the 2, to the 3, to the 4, to the 5, 0, 5. There's the 10, w to the 15, and so on. And then this is w to the 6, w to the 0, 6, w to the 12th, w to the 18th, and so on. And then this is w to the 0, w to the 7, w to the 14, w to the 21, and so on. And so you can see this matrix here of these w values is just this DFT matrix, this discrete Fourier transform matrix, and multiplying this by this matrix performs the Fourier transform as a simple operator. That's not a bad spot right here. So you can see as I get this matrix bigger and bigger, w to the 0, w to the 1, w to the n minus 1, and then down here, w to the 0, w to the 1, w to the 2, w to the n minus 1, and so on. And in the limit, as I let n increase without bound and make this matrix bigger and bigger, you can imagine it approaching the continuous Fourier transform, where this thing here is just a row, DC across the top, one cycle of a sine wave here and a cos wave, and then 2 cycles, 3 cycles, 4 cycles, and so on, and keep going more and more cycles. Now, there's something called FFT shift. Fast Fourier transform shift that shifts the order. It makes sense a lot of times. The way that matrix works to multiply is it puts the DC component at the left, and so you've got 0 is here, and then you've got small positive frequencies here, 1, 2, 3 for the 8 point, 4, and then 5, 6, 7 by the Nyquist rate. These frequencies, 7 is a lot like minus 1, 6 is a lot like minus 2, this is minus 3, and this is plus or minus 4. It's the same right in the middle. So in some sense, this is the middle of the thing, and so it makes sense to flip the left and right sides of this. It makes sense to reverse the left and right sides to put 0 at the origin. So it makes sense to swap this and put right here, 0, 1, 2, 3 right here, and then take these points over here and put them, and this is just whatever the middle value, and then put them -1, -2, -3, and -4 over here. So if I have these data points, say that's at the DC, that's 0 hertz, 1, 2, 3, and then 4 is the one that's plus minus 4 really, 5, 6, 7, and say these are back up. So this is plus or minus 4, 5, 6, 7, 0, 1, 2, 3, plus or minus 4, and then let's say this is negative 3, negative 2, negative 1. What I want to simply do is just remove these here and replicate them over here. Put them over here. You know, put this sample over here, put this sample over here, this sample over here. So now I've got minus 1, minus 2, minus 3. These are the frequency components, you know, and then I of course I get rid of them, and then I'll put the minus 4 over there as well, because what we typically do is just get rid of these 4 samples at the right here and just move them over and put them back here. Now it's somewhat centered at the origin with the extra point out to the left. And so now that's typically how we arrange them when we do an FFT. So if we want to get the matrix to perform that operation, we want that to happen in time and in frequency. So we'll take the rows of the matrix. So if this is the Fourier Transform matrix, what we in a sense do is cut it in half and put this part at the bottom and that part at the top, and then also cut it in half this way and put this part to the left and that part to the right. So and our function, you know, now is, we can think of it sideways as, you know, this is negative 4, 3, negative 2, negative 1, 0, 1, 2, 3. So that's negative 4, negative 3, negative 2, negative 1, and 0, 1, 2, and 3. And so in some sense that's our function here, is this, you know, column vector that it gets multiplied by, and then the result is over here, whatever that function is. And so that's typically how the matrix is arranged. And so what we would do is write the whatever the values are in here. In the case of just a very simple case, 2 by 2, 1, 1, 1, 1, and 1, 1, 1, negative I, negative 1, coming around here, down like this, and then up, positive I, and then negative 1, plus 1, negative 1, and then this one here is going to go I, negative 1, negative I. And what we simply do is take these and flip them this way and turn them this way. So this quadrant goes over here. So we've got 1, 1, negative 1, and I. This piece goes over here, say in a new matrix. I'm going to arrange them in this fashion. And then this quadrant goes up here. 1, minus 1, 1, 1, and I. And then this quadrant, 1, minus 1, negative 1, negative I, goes over here. And then this quadrant, 1, 1, 1, minus I. So you can see now the DC component is close to the middle. Not exactly the middle, but close to the center. And so now that's DC row, and also the order in which these are. The center of this one is here. So the center of this thing is roughly in the center. And of course, as these matrices get bigger, the center comes close to the center. So your DC component will be in the center. And of course, if it was an odd number, if you had a 5-point DFT, the DC component would be right in the center. With an even number, there is no center. So it's just simply just slightly to the right of and below center. And if we shift the 8-point Fourier matrix, it's 1, 1, 1, 1, 1, 1, 1. I'll draw these all as vectors here. We just shift this. We just create an 8 by 8 grid here of vectors. We just create an 8 by 8 grid here upon which there's going to be vectors. 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 sort of grid points at each of these. So this set of vectors, so this is going to be, these are all going to be 1s, just pointing to the right. 4, 5, 6, 7, 8. And then these columns are all, this column is all 1s. And then this will go clockwise slowly by 45-degree increments. By 1/8 of a turn. Each of these is 1/8 of a turn. And then you can see the next row by 2/8 of a turn, which is 1/4 of a turn each time around. So this is 1, -I, -1, plus I, and so on. And then these will go by 3/8 of a turn. So 1, 2, 3/8 of a turn, and then 1, 2, 3/8 of a turn, 1, 2, 3/8 of a turn. And then this will go by 4/8 of a turn, which is half a turn, so they'll just alternate. So this is right at the Nyquist frequency, where it's aliased to the point where you can't tell whether it's a positive or negative frequency. And then these will go 5/8 of a turn. And if you look at 5/8 of a turn clockwise, which is negative 5/8 of a turn, 1, 2, 3, 4, 5, that's the same as going counterclockwise, which is a positive frequency. That's the same as going counterclockwise by 3/8 of a turn, which is a positive frequency. So like this. Another 3 counterclockwise. 1, 2, 3. And then another 3 counterclockwise. 1, 2, 3. 1, 2, 3. And so on. And then the next row we go 6/8 of a turn clockwise, which is 3/4 of a turn clockwise. 3/4 of a turn clockwise, 1, 2, 3, is the same as 1/4 of a turn counterclockwise. So that's 1, 1/4, another quarter counterclockwise, another quarter counterclockwise, another quarter counterclockwise, and another quarter counterclockwise. And then finally 7/8 of a turn clockwise, 1, 2, 3, 4, 5, 6, 7 is the same as 1/8 of a turn counterclockwise. So negative 7/8 frequency is the same as plus 1/8 frequency. So we go like this, just counterclockwise in 8ths. So you can see now that we got this pattern where this is 0 frequency. This is negative 1/8 fractional frequency. This is 8 samples of negative 1 cycle. And this is 2/8, negative 1/4 fractional frequency, negative 3/8 fractional frequency, plus minus a half fractional frequency. And then we'll say that this is plus 3/8 fractional frequency, plus 1/4 fractional frequency, and plus 1/8 fractional frequency. So if we look at which way these are going, the way that we describe this is 0 fractional frequency of each of these rows. That's 0. And then negative 1/8, negative 1/4, negative 3/8, negative 1/2, which is equivalent to plus 1/2, and negative 5/8, which is equivalent to 3/8, negative 3/4, 6/8, which is the same as plus 1/4, and negative 7/8, which is the same as 1/8. And so you can see it makes sense again to swap. If we take these rows, take this group of 4 rows and put it up at the top, and this group of 4 rows and put it at the bottom, again it puts the DC near the center, and then it puts the positive frequencies up on this side and the negative frequencies down on this side, which kind of makes a lot of sense. And so if we do that ordering, I've got another chalkboard here. Love that chalkboard so much, you know. And now let's open up another one. If I take this here, and I'm going to have my 8 grid lines, 1, 2, 3, 4, 5, 6, 7, 8. I'm going to make this all on the same grid. 1, 2, 3, 4, 5, 6, 7, 8. And then I'm going to put on here, I'm going to flip these rows and columns so that DC row will go along here. And then similarly, we're going to flip this over here, so this column will be the fourth column over. 0, 1, 2, 3, and 4 is going to be like this. And likewise, this submatrix here, this quadrant, is going to move over to here. And then finally, this row is just the alternating. So this is the most fractional frequency. Just a fractional frequency is a half right at the top. And that pattern continues over to here, of course. And likewise, this column here of a fractional frequency is a half, continues to over here. So this column is now over here. So you can see the highest fractional frequencies, the ones furthest from the origin in absolute value, the highest ones are at the periphery of this matrix. What was in the upper right quadrant will now come into the lower left quadrant. So you just continue that same pattern. The fractional frequency of this row is plus 1/8. Fractional frequency of this row is plus 1/4, and the fractional frequency of this row is plus 3/8. So this one will also go 3/8 over. So it goes here in a positive direction, which is counterclockwise. So it goes 1, 2, 3. So it's going to go like that, and then 1, 2, 3. So the next one goes up, and then 1, 2, 3. So the next one goes like this, and then continues 1, 2, 3, and then it's to the right, and so on, and continues 3 units counterclockwise each. Likewise, we're just continuing the pattern into here. So this is a fractional frequency of 0, and this is a fractional frequency of minus 1/8. So it's going to go clockwise 1/8 of a turn, clockwise 1/8 of a turn each one. 1, 2, 3, 4. It's going to continue clockwise, clockwise 1/8. Clockwise another 1/8, and clockwise another 1/8. And if it went one more past here, it would be back to where it started again. And so likewise, this one over here is a fractional frequency of -1/4, so it's going to go clockwise 1/4 of a turn each time. And then from there down to here, down across here, and up to here. And then finally, this is a fractional frequency of -3/8. So it's going to go clockwise 3/8 of a turn, 1, 2, 3, and so on. And then 1, 2, 3 like this, and then 1, 2, 3 like this, and then 1, 2, 3 like this. So this is our Fourier operator matrix. When we multiply this matrix by the signal, by some signal, it does the Fourier transform and shifts it into the proper ordering. So this is the shifted Fourier operator rather than the original Fourier operator. So this is the discrete Fourier transform here, and this is like the shifted version of the discrete Fourier transform operator. This operator embodies or builds in that shift in both the forward and inverse transforms, because the inverse transform is just the inverse of this matrix, with the scale factor, of course, accounted for.